Hello, my name is Kent Hogan. I'm from New Zealand, and this is my solution to problem number one, invent yourself for the COVID-19 Young Physicist Tournament. I'm not so young, but I'm doing it anyway. So the problem states, working at home and maintaining appropriate social distancing at all times, design and build a Rube Goldberg machine to perform a menial task. Maximize the inefficiency of your machine. So just to define some of the terms, appropriate social distancing is a minimum of 2 meters from anyone not in your household. I'm the only one in my household at the moment, so I'm good. A Rube Goldberg machine is a series of interacting objects that perform a task in an overly complicated way. A menial task is something that I really could do by myself, but I just can't be bothered. And maximizing inefficiency is to waste as much energy as possible. So first of all, I'm going to define my menial task. Uh, you know how when your computer freezes up or you need to restart it and you need to open the task manager, which is you need to press Control Alt and Delete. But if you've got your mouse in your right hand or a drink or something, it's really awkward to do it with one hand. So my task is to press Delete. Okay, so to define inefficiency, first of all, I'm going to talk about what efficiency is. So efficiency is the percentage of expended energy that is used effectively. So to express that as a percentage, we just take the effective work done and divide that by the energy that was actually expended and multiply it by 100. So if we did a task that involved 5 joules of work, but we actually used 50 joules of energy to do it, then the efficiency would only be 10%. Inefficiency is the percentage of the expended energy that is wasted. So we define it as 100 times 1 minus the effective work done divided by the energy expended. So in that same example, if we did 5 joules of effective work but expended 50 joules of work doing it, the inefficiency would be 90%. So this is the machine. Okay, just to make a few of those last stages clear, because they weren't too clear in the video, because they happened quite quickly and I couldn't follow it fast enough. At the very end there's a cricket bat that swings down and hits a ball, which you didn't actually see in the video. The ball hits the wickets and the wickets fall over. As the wickets fall over, there is a string tied to them. They release a mass that is attached to a string. It slides down the string, hits another little stack of masses, which releases a cotton thread underneath them, and then another mass hanger that's hanging just above the delete button with a lump of blue tack on the bottom falls down and hits the delete button. So in that machine, there are 31 different stages that all transfer energy along through the system. So in virtually every stage, what's happening is that you have a transfer of gravitational potential energy, which is the energy expended. So each stage has some gravitational potential energy in it to start with, and that is converted to kinetic energy, which is the effective energy, which gets passed on to the next stage, or at least some of it does, and you have heat loss, so energy being lost effectively from the system. So taking our definition of inefficiency from before, it's 100 times 1 minus the effective work done divided by the energy expended. The effective work done is just the force multiplied by the distance to actually complete the task of pushing the delete button. And the energy expended will be the sum of all of the gravitational potential energies. So we can express the inefficiency as this. It's 100 times 1 minus force times distance, where force and distance are those required to complete the actual task,
divided by the sum of mgh, where m is the mass of all of the elements in the machine, and delta h are the height changes of all of the elements in the machine. Now, not all of the stages actually have energy input. Some of them just transfer energy from one stage to another. The ones in black are ones where there was no, or at least negligible, energy input into the system. They just transferred energy from one stage, from the previous stage to the following stage, and activated energy that was in the next stage. So those will be excluded from the actual calculations that are going to be done next. So to actually calculate the energy changes that are occurring in each of the stages. So there are three main types of transfer going on, which are all basically the same thing. There are stages where something falls, so it starts high, moves down and ends up at a lower point. There are stages where something is on a ramp or sliding, and it starts at a higher point and it ends up at a lower point. And there are a few stages that are into the pendulum, so it's starting at a high point and it swings down and finishes at a lower point. And all of these types of stage, we have something that's starting at a high point and finishing at a lower point. So there is a height change in that. And for all of these different types of stages, we can calculate the energy change by using mg delta h. There's another little complication with some of the domino stages, like there was domino blocks and also books, in that the center of mass, when it falls, does not end up completely on the ground. It ends up propped up by the one ahead of it. So the height difference will be this height difference. So the difference in height from where the center of mass was when it started to where it was when it ended. And again, we can calculate the energy difference using mg delta h. So if we go through all of the stages that actually had energy differences, these are all of the energies in the actual system. I'm going to put a graph up in a second. So in terms of determining the masses, the large masses were measured with kitchen scales. If it was above about 200 grams, the smaller ones below 200 grams, I used a torque balance beam with a known mass on one end and the unknown mass at the other end, and I moved them until they balanced, and then by calculating the torques, calculate what the mass was for the smaller ones. So adding all that up, we get a total mechanical energy expended of 26.9 joules within the system. Just to see how that breaks down, this is each stage separated out. You see there's a large collection towards the end where there was a lot of either the ones that are quite large are ones that were either there were lots of elements, such as the dominoes or the books, or there were quite heavy elements involved, such as the hammers falling, or where there was a large height difference, such as the toy plane. Oops. Okay, now, so the total mechanical energy that's been expended is 26.9 joules. So to calculate the inefficiency, we need to know how much effective work was actually done. So to do this, if this is the delete button on the computer, what I did was I placed a mass on top of it. I found what the minimum mass was that I could place on the button for it to actually depress. And then I measured the height difference. Now, for that to actually work, the minimum mass that was needed was about 80 grams, which was actually more than I was expecting. And the height difference was 1 millimeter. So the work done is equal to the change in gravitational potential energy of the mass, which is 7.8 times 10 to the minus 4 joules. So not very much energy. So to actually calculate the inefficiency, we've got our formula from before, and we can plug in the numbers we now have. The work done was 7.8 times 10 to the minus 4 joules, and the actual energy expended was 26.9 joules. That gives the machine an inefficiency of 99.997%, which is quite inefficient. But the problem does ask us to maximize this. Now, there was not only energy expended in the machine itself, there was also energy expended in the assembly of the machine. Now, this is going to be an approximation, but it's worth looking into. So a bit of a Google search came up with a value of 2,000 calories, which is 8,400,000 joules of energy a day for an adult man. Okay? Now, I spent 2 days building and testing the machine. So let's assume I spent 10% of the energy on those days working or thinking about the machine. That's probably an underestimate given how much time I spent on it, but let's just go with it. So that means the energy that I use in the assembly is 8,400,000 times 2 days times 10% is 1,680,000 joules. If we add that into our inefficiency calculation, so 26.9 joules used by the machine itself and 1,680,000 joules expended by me, that makes the inefficiency 99.9999995%. It's really inefficient. We can take it a little bit further though, because in a practical sense, my laptop was fine. I didn't actually need to open Task Manager. So the effective work done was actually 0 because it was a task that was unrequired. So the inefficiency practically was 100%, which is maximal inefficiency. So just to review the problem, working at home and maintaining appropriate social distancing at all times, design and build a Rube Goldberg machine to perform a menial task. Maximize the inefficiency of your machine. So to conclude, gravitational potential energy is expended in each stage, which is converted into kinetic energy, being passed on to the next stage, and a lot of it is lost as heat. And the inefficiency can be expressed as 100 times the 1 minus the effective work done, force times distance, divided by the energy expended, which is the sum of the MGH of each stage. So to maximize the inefficiency, you want to maximize the energy expended by the machine by maximizing the number of stages, maximizing the mass of the elements, and maximizing the height change of the elements. And you want to minimize the effective work done. For my machine, that was 99.997%. But you can also increase the inefficiency by spending a stupidly long time working on it if you include the amount of energy that was spent doing that. For me, if I included that, it became 99.9999995% inefficient. And the other way to really make it inefficient is to perform a task that doesn't actually need to be performed. So practically, the inefficiency of my machine was 100%. Thank you very much.